Okay, we are good to go. So, welcome all to this week's Majorana-Raychaudhuri seminar series. Today, our first speaker is Christoph Englert. He's from University of Manchester, UK, and the title for his talk is Effective Theories for Weak Scale and Beyond. So, yeah, thank you so much for coming to this talk and giving the talk. So, yeah, you can start. Thank
Yeah,
you.
thank you very much for inviting me. It's a great pleasure to come to you remotely from rather murky day in Manchester. I just joined the University of Manchester. Originally, well, not originally, but I was based in Glasgow before that, so until a few days ago, really. I want to talk about effective theories for the weak scale and beyond. So what I'm mostly interested in is Higgs physics and Higgs phenomenology, in particular at colliders, but also a little bit in the astrophysical context. And it's probably fair to say that even after, good 12 years, 13 years of after the Higgs discovery, we don't quite yet understand the nature of but there is a sort of a deep expectation that it should be connected to some more fundamental principles and more deep theories of particle physics. And then that's kind of highlighted by the fact that there's a plethora of serious theoretical problems in the standard model, but especially connected to the weak scale. And I'm sure you're all familiar with the fine-tuning problem. And in a way, we've been there already, and fine-tuning problems always tell us that there is something happening that we don't yet understand. So if we go back, to sort of 200 BC, when the first planetary system was developed by Ptolemy, um, where the Earth was really in the center of the universe, as it were, that was a highly fine-tuned affair. And but people were pretty happy with it to accept the fine tuning, as we are pretty happy at the moment to accept the fine tuning of the Higgs sector and the electroweak scale. And it was not until, a good 15, 1700 years later, when Copernicus used that fine tuning as a partial motivation to actually resolve the issues of Ptolemy's system by considering the sun really at the center of the planetary system, thereby resolving the fine tuning really by making or by understanding it as as an effect that comes about from the moving platform that is the Earth. So, in a way, we are dealing with a similar situation today. Every fine-tuning problem is sui generis, so it sort of exists in its own right, and we obviously can't use Ptolemy's and Copernicus' ideas to resolve the issues that we face in particle physics now. But what we see is that on the one hand side, we have these theoretical issues or question marks that we don't quite know yet to address, especially in the light of absence of new physics at the LHC, for instance. But at the same time, we see large consistency of data with the standard model expectation. So I have highlighted here some early atlas measurements of various Higgs production and decay channels. And you see this is typically the statistical picture that we would expect if a theory is right. So there is a scatter, there's uncertainty, but overall it looks rather appealing for the standard model, if you like the standard model. So in the spirit of Copernicus versus Ptolemy, perhaps a different way of tackling this is looking at data from a different angle. Perhaps somewhere the solution to this exists in how we interpret that data. And this is really what I want to focus on in the next 40 minutes or so. So I will discuss beyond the standard model sensitivity from particularly interesting processes that can become accessible at the high luminosity LHC to relatively high precision. And then there, starting from these, I want to draw some parallels with recent ideas of how to approach scattering processes from a point of view of geometry and field space, how that connects with perturbativity and renormalizability, and how phenomenological patterns in the bosonic sector might actually give us some clues as to where new physics might hide. And if time permits it, I will also talk a little bit about how to use these ideas to actually revive some of the most or best motivated models for dark matter that are really simplistic, so Occam's razor approaches to dark matter that are otherwise under pressure. But with these effective field theory approaches, we might actually gain some breathing space that we can then use to hopefully discover new physics. So, what particle physics theory really is about in this new age of artificial intelligence and data science, particle physics really is a prediction of correlations. And to go away from the standard model expectation of these correlations, there are various approaches on the market. Of course, you can look at concrete scenarios, so you can study concrete Higgs sector extensions or uh, extra dimensions, and there's a plethora of concrete models out there. But if you want to look at it from a more bottom-up perspective, where the standard model sort of sits there as a key successful ingredient, and you want to look for new physics in a more agnostic way, one way of doing this is through the application of effective field theory. And there are essentially two different operating principles on the market that I just want to quickly compare. So on the one hand side, you have standard model effective field theory, where you build higher dimensional operators, as is indicated here, beyond the dimension 4 operators of the standard model by using the particle and field content of the standard model itself. And for the Higgs sector, that means in particular, you construct these higher dimensional operators from the Higgs doublet. So that kind of gives you a building hypothesis or building constraint of how these operators might look. So that comes with its own challenges, but with its own simplifications as well. So in standard model effective field theory, you typically deal with the clear power counting, so that scale lambda matching calculation. Once you source these higher dimensional operators by matching them onto a concrete scenario, those lambda scales, they will typically be particle masses. For instance, the connection of the Fermi constant with the W mass is one example of that. And if that scale is high enough, you have a clear hierarchy between these different interactions, and the expansion is typically well behaved. You have comparably few bosonic parameters. Of course, flavor is one of the big unknowns in the standard model of particle physics that I do not have the time to talk about today. But when we look at the bosonic sector in isolation, then actually there is not that many operators that you can write down at the dimension 6 level at least. And one of the reasons for uh, that this relatively small number of these operators is that there are tight correlations across Higgs multiplicity and multiplicities, because that's really due to the fact that we build these operators using the full SU2 Higgs doublet. And we work in a manifestly nonlinear electroweak vacuum, so it's a standard model electroweak symmetry breaking approach. And that has typically non-trivial technical implications. So you need to worry about tadpole diagrams and so on and so forth. I don't want to go into the details too much of that. If you want to summarize this in one sentence, then standard model effective field theory, if you want to approach new physics from that perspective, that assumes that the standard model is a good reference point in the infrared of your theory. And that's probably a fair point when we look at the data as it presents itself to us at the minute. On the other hand, you have what is called Higgs effective field theory, which is really kind of reviving the old technicolor or chiral perturbation theory approach. So that approach is essentially built by looking at some ultraviolet theory that only gives us the would-be Goldstone bosons that couple to the gauge bosons in a certain way that gives the mass eventually. So we trigger electroweak symmetry breaking, but without making concrete reference to how these Goldstone bosons arise, but we write them down in an effective approach directly using the Callan-Coleman-West-Zumino approach. So there is this tight relation, at least formally, with technicolor or chiral perturbation theory. And the Higgs boson, the physical state that we've observed with 125 GeV, in this framework then plays the role of the technique sigma. So it's an additional isosinglet scalar that sits there, and its couplings happen to be exactly the way how we measure them, exactly how the standard model predicts it. But in principle, they can take on any value. That, of course, comes at the price of a large number of parameters. So you can now decorrelate different Higgs multiplicities. And here you really have to use collider data to inform these different operators. So for each individual operator, you in principle have to have one different measurement, and you have actually a very large number of these bosonic parameters, but also a lot of flexibility. And this is really what I want to highlight. So just making the comparison against how the vacuum of these two different field theories behave, here in Hef, we have sort of coarse-grained away the mechanism of how the electroweak vacuum is achieved. And you would naively think that you have many, many operators that contribute this, so that should create technical difficulty. And of course, it's not easy. But actually, because the Higgs is a manifest singlet in this formalism, a lot of technical simplifications come about. So even if you do not like Heft as a standalone theory, it has technical aspects that make it rather attractive when you're interested in precision calculations. And on top of that, Heft always contains MEF. So you're only maximally one redundant field redefinition away. So you can choose your parameters in such a way that any correlation that you get in SMEF can also be achieved with Heft. So from that technical perspective, Heft contains. And if you all want to boil that down into one simple sentence that kind of references this SMEF sentence above here, that would be that standard model electroweak symmetry breaking is perhaps too limiting. So we treat that in Heft as an effective approach, and then we run with it. I should say, by the way, that if you have any questions, then please feel free to interrupt me. There should also be some time at the end, I suppose, for questions. And that correlation, how we get Heft mapped onto SMEF, that has been a very active area of research over the past few years, and I'll just give you a bunch of that you can follow up on. What I want to focus on really in the next few slides is exactly these points. So I want to tell you that new rare processes that we just got access to at the Large Hadron Collider, they actually will be able to pinpoint exactly these differences between a SMEFT and a Heft approach. And perhaps there is still space in the data, there's still enough room in the data for that to show up, that we actually see that there is perhaps a more Heft-like structure that presents itself when we look at the electroweak scale rather than a SMEFT-like scale. So that's purely data-driven. Whether we believe that or not, that's a different question. But eventually data will decide that. So what are the typical processes that one can look at? Of course, there's the production of the Higgs boson at the LHC. This is how we have discovered it through its decay phenomenology as well. And this decorrelation of different Higgs multiplicities, what I really mean by that is the comparison of single Higgs observables with double Higgs observables. So you can produce two Higgses and then they decay, but of course these are different production mechanisms. They are a lot rarer than single Higgs production. So the dominant gluon fusion Higgs pair production cross-section is 30 femtobars. So this is not an awful lot, especially when you take into account that we have to decay the Higgs and we have to find it in overwhelming backgrounds. So we're just starting to become sensitive to these major production mechanisms. WBF here, weak boson fusion, that's a very interesting process in its own right, which has a very distinct phenomenology, which is very non-QCD-like. So it's kind of easy to separate this from the contributing backgrounds at proton collider experiments. However, that cross-section is very, very small. It's around 1 femtobarn before decays. And here, top pair associated Higgs pair production is typically below 1 femtobarn in very, very busy final states, so very difficult to set constraints on that. And CMS has just released the first analysis that tackles that. Of course, we are still very far away from standard model sensitivity there. What I really want to focus on is this particular process because it actually provides a clean phenomenological window into the dynamics of single Higgs versus di-Higgs that we can then use to compare SMEF versus Heft, but also gain geometric insights into the structure of beyond the standard model theories that might create these correlation changes away from the standard model expectation. So just to highlight what I mean with correlation multiplicities. So in the standard model, the direct coupling of two gauge bosons to one single Higgs actually arises diagrammatically from taking the, the quartic interaction of two Higgses with two gauge bosons and setting one Higgs to its vacuum expectation value. This is exactly how it works when you expand out the Higgs kinetic term around its vacuum expectation value. So diagrammatically, this is how you obtain these single Higgs vertices compared to the di-Higgs vertices. And of course, that means that the theory highly correlates single Higgs physics in these weak channels between single Higgs observables and di-Higgs observables. So in SMEF, these are highly correlated, and in HEFT, they are not correlated at all. And the question really is that well, the sort of, after all this spiel, the answer that I want to provide is to the question whether there is any new physics gain that we can draw from allowing these correlations to vary. When I say it's a very distinct process, it's also very, very clean from a QCD perspective. So typically at collider experiments where we collide protons, QCD is always kind of our big enemy um, by creating busy final states, but also by creating large uncertainties from the theoretical point of view. So we don't necessarily have all higher order corrections under control. And weak boson fusion here is very, very different. So when I show you this sort of the arrow band here is when we vary scale uncertainties as we traditionally do in hard scattering calculations to assess as a community kind of consensus how big of an uncertainty is associated with the theoretical calculation. So you see the leading order band here is in blue. And the next to leading order band, when we include higher order QCD corrections, actually becomes almost negligibly small. And that really is due to the fact that a lot of the QCD corrections to these diagrams can actually be absorbed into the PDFs. In a way, this is double deep inelastic scattering here. So there's a reason why this is such a clean process, not only experimentally, because these guys will give rise to back-to-back jets and no QCD activity in the central part of the detector. So you can use that to really isolate this signal process from whatever contributes to, as a background. But also theoretically, the interpretation of that clean measurement is not hampered by any large QCD uncertainties. And many groups have done that, and my student Rishik Naskar has done this calculation together with me and Dave Sutherland in 23 as part of the work that I'm showing you here. So, how do we look for new physics in such a final state? Well, the Atlas and the CMS experiment, they typically look at templating Feynman diagram topologies. That doesn't come without risks, but this is how the approach works. So you typically rescale the standard model-like couplings here of the gauge quartic by a flat factor kappa 2v. You have a rescaling of the trilinear Higgs coupling by a kappa lambda and the single Higgs couplings by a kappa v. And then, of course, when you have diagrams like these are rescaled by kappa v squared. You trace all of this through to the experimental data. And currently, the best constraints that I was able to find are here in kappa lambda from this process in minus 3.5. That's not the tightest constraints. The tightest constraints on kappa lambda are set from gluon fusion, so the other process that I showed. But this is really focusing on this particular process, and kappa 2v sits somewhere within 100%. And of course, the more data we'll get, the more precise these measurements will become. So the question that I'm trying to answer is what can be learned from that measurement, especially when we would expect in the standard model that these couplings are highly correlated, kappa 2v and kappa v, by standard model gauge invariance. These coupling, of course, they do nasty things to the theory, and we'll discuss this in a little bit as well. But even at an early stage, or especially at an early stage in data, when data quality is poor, they're actually helpful figures of merit to gauge if we are in a perturbative or non-perturbative regime, which really tells us, do we have a chance to do something interesting with that data as of this point, or do we have to wait until more data is collected and its quality is better? And of course, people have been looking at this from a kappa lambda perspective because this is a little bit more when you think about early universe phenomenology and strong order phase transitions. So the Higgs trilinear coupling is of central importance there. So people looked into popping these Higgs self-coupling rescalings like this guy here into a loop, and that changes the Higgs coupling. So it adds to the renormalization of the Higgs, and thereby you can trace it into other observables, for instance, in the modification of the Higgs branching into two photons, which is a very clean channel, and that's a one loop suppression. And those of you who are a little bit familiar with electroweak precision, famous Peskin-Takeuchi parameters, the Higgs propagator in its self-energy correction enters there at the two loop level, and you can also use electroweak precision data to then look for modifications of kappa lambda. And all of these processes sort of give you the same sensitivity that tells you that your data is just not good enough, okay? Because you're comparing different loop orders and they all give the same result. That puts a little bit of strain on the suspension of our quantum field theory. So that's what I mean with figures of merit. But again, the question really is, what's the merit of these searches in the first place when we know that these couplings here in the standard model are pure gauge-like and they are highly correlated with kappa V? What can we learn from these? And you could think of, okay, I mean, I'm doing something rather nasty here to the theory. I change one part in the covariant derivative, whilst I keep another term exactly standard model-like. And that should kind of manifest itself in immediate problems. So perhaps we can look at if there are any issues with that Atlas interpretation, or the Atlas and CMS have done it as well, of course. Are there any issues a priori with that? So we can go back to electroweak precision physics. You can look into corrections to the T parameter, which is a measurement of custodial isospin violation, essentially how big the W and Z mass ratio departs from its relation in terms of coupling strength is. And as long as we take kappa 2Z, so if we align these coupling rescaling factors across the Z and the W bosons, then we are golden. No problem arises, and at leading order, the T parameter is exactly zero. So we do not have any constraints from electroweak precision physics if we kind of change these quartic interactions in an aligned way between the W's and the Z's. Can then ask the question, does unitarity break down? And unitarity will actually feature quite strongly in the remainder of this talk. And it turns out that it doesn't really break unitarity. So Atlas are setting a constraint which holds for the entire, where perturbativity holds for the entire energy regime that they probe. So they are never resolving a unitarity violating scale in that measurement. So in other words, the measurement and the constraint that they have provided is robust, and we have no problem with the interpretation from the point of view of perturbative unitarity. So now where it sort of falls apart is really when theoretical um, calculations come in. So for instance, we can look at radiative corrections to the Higgs decay into two Z bosons, and in next to leading order, you will get exactly these new diagrams here that feature these gauge quartic interactions. We have to choose a renormalization scheme. So this is the on-shell renormalization scheme, and I introduce these zeta parameters to measure how much we go away from the standard model expectation. You can do the calculation. It's rather lengthy and not too inviting, say, but I just want to sort of give you the highlight of what's happening here. So when you do that next to leading order calculation, you renormalize everything. You still have that delta factor, which is in dimensional regularization, the 1 over epsilon pole, which tells you that you have to renormalize something else here. And that's good news because we can use that extra renormalization to redefine the single Higgs coupling to two Z bosons as a function of kappa 2V. In other words, we can measure rescalings of the gauge quartic interactions, the gauge Higgs quartic interactions by making very precise measurements of single Higgs physics. So that's great. That's exactly what we want in order to kind of get a really fine-grained picture of the dynamics of the electroweak scale. However, in the standard model, this comes at a price, namely, we have done the calculation, or I've done the calculation here in arc psi gauge, and that delta factor, that 1 over epsilon pole that sources a coupling change in the single Higgs couplings becomes gauge dependent. And that tells us that essentially that calculation or that theory has lost all of its physical characters. Now our actual observables are gauge dependent. And of course, that's expected because we have done something terrible to the standard model Lagrangian by taking one part, changing that, and leave everything else exactly standard model like. And of course, gauge invariance is hardly broken here. Well, is broken explicitly, not hardly, just explicitly. And that shows up here now that we've lost perturbative control over this. So it seems to suggest that these kappa 2V measurements are actually not terribly meaningful when you interpret them in a standard model or a standard model effective field theory context. Where they make sense is exactly in this Higgs effective field theory approach, where the Higgs is a custodial isosinglet and you decorrelate all the different Higgs boson multiplicities. And that just comes about by taking this Lagrangian here, which is really the chiral perturbation Lagrangian. You have the kinetic terms here for the W's and the hypercharged fields, fermions, and the Yukawas. And this guy here is nothing else but the Goldstone kinetic term using the CCWZ approach. And that is stressed with this FH kind of flare function, as it's often called in the literature, which gives rise to sort of a power series expansion in different Higgs monomials, and they are all completely decorrelated. So this guy here is gauge invariant, and the Higgs is a singlet. So these zeta 1 and zeta 2 parameters are completely independent and arbitrary. And you can also write these things down in terms of Heft operators. They look kind of complicated and not too illuminating. But what happens there in terms of physics and calculational details is that the Higgs is gauge independent, straight out of the box. This is how we have set it up. The vacuum is gauge independent. It's the masses that the gauge bosons get are gauge independent. And that is typically not what happens in the standard model or standard model effective field theory. It depends a little bit on how you treat your tadpoles, but this this happens here automatically. I don't want to go into too much detail about this, but just flag this as particular technical advantages. And within that framework, we can then really set constraints on kappa to V by making very precise measurements on kappa V. And now I just display this here as functions of these zeta parameters, where zeta measures the departure from single Higgs physics and zeta 2 measures the departure from di-Higgs physics. And 16 pi squared here is the loop factor that naturally arises when we interpret single Higgs phenomenology as is done here. And of course, this is how things look now, roughly, and this is how they will look like in the future at the high luminosity phase of the LHC. But of course, this 16 pi squared is rather discouraging, and it just comes from the fact that within this Hef parameterization, we really have to make precise measurements of all the involved couplings through new input data. And new input data here really is the measurement of double Higgs production in weak boson fusion that I've been discussing just a few slides ago. And typically that process that you will be able to measure relatively precisely at the high luminosity phase, that will set the tightest constraints on kappa 2V and thereby on zeta 2 in the future. And we've done a bunch of studies that show this, and we used artificial intelligence to also enhance the selection, fairly standard these days. And you see that actually the direct sensitivity that you'll get is much bigger than the indirect one, which is also a good thing because direct sensitivity, if things are under perturbative control, they will always give the more dominant constraints. So after we clarified this, so maybe we can think about what is the physical value in looking for these coupling departures in isolation. And this is where unitarity features very strongly. So there are unitarity relations. So when you look into longitudinal WH scattering, where S is the center of mass energy of this 2 to 2 process, you'll see that in the high energy limit, unitarity conservation requires you to have exactly that relation of kappa 2v and kappa v squared, which is an imprint of the renormalizability of theories and the standard model in particular. And one way of checking this is when you write down your standard model and you extend it with a singlet scalar, so the Higgs portal, as it were, you essentially introduce a new rotation angle between a new scalar and the physical. And these are the coupling modifications that you would see in such a process. Single Higgs physics gets one mixing angle. The gauge quartic gets a cosine squared, and you plug this into this equation, you directly get zero. And that is the sort of the theory telling you that it is renormalizable. And of course, when we change these couplings away, kappa 2v from kappa v squared, we reintroduce unitarity violations. So we actively enter that arena of effective field theory. It turns out that actually, when you look at these scattering amplitudes, they can be as sectional curvatures of the electroweak symmetry breaking manifold, and that's work by Rodrigo Alonso in collaborations in 2016. And what underpins this really is the Goldstone equivalence theorem. So the scalar manifold kind of shapes how the W's and the Z's couple to the physical Higgs at high enough energies. And one particular nice example of how that geometric insights really shapes the phenomenology that we see is composite Higgs theories, where the minimal composite Higgs model here, MCHM, SO5 to SO4 coset, which can be represented by the unit sphere in well, a four-dimensional unit sphere. Okay, and that directly gives you relations of kappa v like this, where xi measures the vacuum expectation value in units of the pion decay constant of this CCWZ construction, and kappa 2v gives you that. So xi is essentially a free parameter that runs from 0 to 1. And for compact groups, so those that are compact spaces, you will always get these relations here, which was showed by Rodrigo and his collaborators. Now, you can say, well, how do I disentangle composite Higgs theories from from single Higgs theories? Well, you can't really. You need that di-Higgs information with an asterisk. So I can always find a xi value here for a given mixing angle. And I need my kappa 2v measurement to really break the degeneracy, because if I identify my cosine alpha through kappa v with a xi value here, then kappa 2v will not match the kappa 2v of the singlet scenario. There will be continuous enhancements, but when you're close to the standard model, you will actually not see that too dramatically in di-Higgs production through weak boson fusion. So you need this measurement, and it directly adds value here. What Rodrigo and collaborators also showed is that you cunningly, by analytically continuing one of these dimensions, you can decompactify, so to speak, your sphere, which is what we always do in the representation theory of the Lorentz group, for instance. And you can extend these coupling modifiers into the positive regime. So you deal with kappa v's that are larger than unity and kappa 2v's that are larger than unity. But of course, you can also look at concrete scenarios. And I have a little table here that doesn't really matter. But what you find typically in these is that kappa v is smaller than unity and kappa 2v is larger than unity. And when we looked at this together with Rishik and Dave, well, we asked ourselves, what's the value, or is there a possibility to actually have scenarios where kappa v is bigger than unity and kappa 2v is smaller than unity? Because that's the quadrant, so to speak, that we haven't covered yet. And it turns out that this idea of geometry really comes into its own at this stage. And that's something that people in general relativity, I know some of you are cosmologists, have been using quite dramatically. Of course, for instance, Bekenstein in 93 looked at the kind of a classification of metrics that are consistent with the weak equivalence principle. And instead of looking at Riemannian geometries, he started with Finslerian geometries, and then got back Riemannian geometries by constraining this Finsler function. And in a way, we can play the same trick in field space, for instance, by adding an additional dimension, an additional scalar, which is typically what's happening in composite Higgs theories, and we give it some profile. So the curvature is no longer constant, but it varies as a function of this additional scalar. And in principle, that scalar can do whatever. And through this metric, we can trace back again what the kappa v and kappa 2v values will be and how scattering processes will look like in our detector. But one working assumption that we chose was that it's actually a singlet under the electroweak group, because then we can freely vary its vacuum expectation value, so to speak, without creating additional havoc in the electroweak sector. And of course, those of you who are familiar a little bit with ADS-CFT and or even inflation, you see that this is very reminiscent of a moduli type electroweak symmetry breaking. So very similar to warped extra dimensions. And this, imposing these ideas, you actually can get back into this lower quadrant where kappa v is bigger than 1 and kappa 2v is smaller than unity, when typically all other scenarios live up here. So this is a highlight, and we made or the money plot, so to speak. So we draw a chart of new physics and how new physics can be kind of charted out by measurements in this kappa v and kappa 2v plane. We also made some extrapolations to the high luminosity phase and whatever might come in terms of collider physics beyond the LHC. And you can clearly see here that that stretches an enormous amount of different scenarios, renormalizable, non-renormalizable. So triplet physics, triplet Higgs physics typically lives up here. Singlet Higgs physics traces out this one line. The 2HDM sits on this line. The composite Higgs model sits here. The extended hyperbolic composite Higgs model sits up there. And the region that we identify through changes in geometry, that is something super exotic that would typically be a composite Higgs model that mixes with a dilaton, which really is the moduli in ADS-CFT. So surprises are possible, but typically these scenarios will have quite a phenomenological imprint on the electroweak scale as well. So we would have seen these exotics that are predicted by these theories already or in the near future. So watch this space. So perhaps in the last few minutes that I have left, I want to kind of go back to the link of this with astrophysics and how effective field theory can tell us a little bit more or revive certain scenarios that are otherwise a little bit under pressure. So one of the theories that I talked about is the Higgs portal, where you take the Higgs doublet here, phi dagger phi, and you couple it to a hidden sector, and you stabilize this S through an additional intact Z2 symmetry. I don't want to talk about domain walls and stuff like that, but there are ways to solve this. So it turns out that when you look at the Higgs portal and you think about strongly interacting interactions, and there's a way how you can categorize them, the next dominant operator in an effective field theory expansion could be this guy here, where you have a kinetic term that's suppressed by a cut of lambda squared that dresses in addition to the standard portal interaction uh, this operator here. So this is the standard portal that I suppose a lot of you are familiar with. And then you have this new interaction. And from the point of view of dimensionality counting, actually this operator is unique at tree level. And one particular scenario that you could write down, also reminiscent of chiral perturbation theory, is coupling the standard model Higgs singlet bilinear operator here to dark QCD through exactly this interaction. And then the only Z2 breaking term that would appear would actually be a Westermino-Witten term. So essentially you take QCD and you directly sandwich it to the Higgs portal in its effective way. And the treatment of this It's a relatively simple Lagrangian, is a relatively simple theory. Doing calculations in it is not so trivial because, of course, you deal with effective field theory. And what we're really interested in is the juxtaposition of indirect measurements that we can obtain, for instance, in the Higgs sector. The Higgs sector will feel these particles bopping about and then nonlinear momentum dependence as well. But of course, we also have direct constraints and, of course, constraints from astrophysics like the dark matter relic abundance. So one particularly interesting scenario is when this dark scalar is light. And that is typically highly constrained by the observation of the Higgs boson as we've seen it. So it is standard model-like. And by adding a new decay component to it, so when that scalar falls below the Higgs threshold, then that will modify all the observed branching ratios and production cross-sections, and therefore that is tightly constrained. However, now we have a new process, a new operator that adds coherently to this decay. So in principle, you can allow for cancellations. And so by arranging these couplings in such a way, and that's always perturbative, it's quite interesting in its own right, you can actually decorrelate um, the Higgs production and decay phenomenology from its interactions with that exotic scalar. And then sensitivity will be shifted into virtual corrections of how the Higgs moves about in space and time. And if you trace this out, actually you see that this parameter region can be constrained through radiative corrections and their imprint in collider physics. So the LHC will be able to probe some regime, and the future lepton collider, such as the FCC-EE or SEPSI, will be able to, of course, give you a much more fine-grained picture, but also processes that measure how the Higgs moves through space and time. For instance, for top production is a very motivated process. We'll be able to set relatively tight constraints on these interactions here, and that's just to highlight that this is possible. So perhaps the most interesting bit is how does that now work with the tension between direct searches and Higgs physics. That's kind of an Higgs observation. So that's typically where these portal scenarios, when you try to understand dark matter in terms of them, that's where they run into problems. And here there's a new region of phase space or parameter space, I should say, that opens up where actually both relic abundance and direct detection can be satisfied simultaneously. That needs carefully arranging parameters, especially for light states, but it's a viable parameter region of this scenario and a viable parameter region of the scenario with direct consequences for the high luminosity LHC and a future precision E plus C minus machine that can measure Higgs properties very precisely. So if that is realized in nature, we will see it perhaps at the LHC here. So this is a coupling deviation, and the horizontal band gives you an impression of the precision that can be achieved. And of course, this condenses down when we go to a precision machine like FCCEE. So we can actually probe the parameter region where dark matter sort of gets revived in this context of strong interactions. We can measure that relatively precisely, or we can rule it out over a wide range, but also observe it in case nature nature chooses to throw such a scenario at us. Brings me to my summary and the conclusions. So the LHC experiments, they are zeroing in on multi-Higgs and jet final states, so we get a lot more data. And this will continue over the next few years. And different EFT approaches that I've touched upon highlight the importance of that data in different ways. And Higgs effective field theory that I sort of quickly introduced but focused more on the phenomenological applications is really a very flexible approach to navigate all phenomenological implications that you could think about in the bosonic Higgs sector. And the theoretical appeal of this is that by making a priori theoretical assumptions, you really limit your view onto that data. And experimentally, on the other hand, we have only rather limited insights into the Higgs potential so far. So we could be in for a massive surprise, and the LHC still has a bunch of aces up its sleeves. And I showed you in the last two slides that this can also have direct relevance for other phenomenological arenas, such as such as dark matter and astrophysics. And that can manifest itself then through new momentum dependencies that should just be not there in ordinary Higgs physics or SMEF-like Higgs physics. It could link to a non-perturbative character of the electroweak scale, but also, of course, then in direct relation to baryogenesis and cosmology. And I hope I gave you in the last two slides sort of a qualitative understanding of how this could come about. Thanks very much for having me, and I hope there's time for questions.